Hello, everyone. I would like to welcome you at the first Fenix Research Infrastructure webinar on HPC and cloud infrastructure for neuroscientists. The speakers for today is Dirk Pleiter and Thorsten Hatter from the Jülich Supercomputing Center. And it's the first webinar of a webinar series that we're organizing as a ICEI Fenix project. I am Nicoleta Chiapidou, and I am dissemination officer at the Barcelona Supercomputing Center. And I'm also in the dissemination team of the ICEI project. And I would like to thank you for attending this webinar. And I would like to let you know that it's being recorded from now on. And the file will be shared later on the website and on the social media, so that you are aware in case you share personal details such as your name or surname or affiliation when you ask a question later on. The structure of the webinar is like this. Dirk will first have a presentation for about half an hour, and all participants will be muted for now. And then in the second half of the webinar, we will have an open discussion, a Q&A where people can ask questions. And this is when we will unmute your microphones and you will be able to ask questions, and Dirk and Thorsten will be able to reply. So I will pass now to Dirk, who can start with the presentation.
Okay, thank you very much. Also, a warm welcome from my side. I'm not sure that it's already sharing. Okay. So as this is the very first webinar of its kind, we plan to have more of them. We would start with giving, say, a brief introduction in where is this ICEI project about and what is the kind of infrastructure which we are going to make available, and also highlight one specific use case just to give you some impression on how this infrastructure could be used, and ideally how this infrastructure, it gives an idea of how the infrastructure could be used by you. And since you want to use these webinars also for providing more technical details, we have then a second part which is then presented by my colleague Thorsten Hatter, which is about the Archival data repositories which we are putting in place within the Fenix infrastructure, which is built on top of the technology which is called SWIFT, and he will introduce you with some of the details of this technology. We will then conclude this webinar by highlighting also what kind of support you can get, and then we will turn into the second part of this webinar where it's up then to you to ask questions, and we will do our best to answer all of them. So the ICEI project is a project which runs under the umbrella of the Human Brain Project. It's, say, if you like, just another specific ground agreement or SGA, where, say, the main actors are 5 supercomputing centers, which you see here on this slide. It's the Barcelona Supercomputing Center in the CEA in France, Clinica in Bologna. Then we have CSCS in Lugano in Switzerland, and we have the Jülich Supercomputing Center here in Germany. This project is mainly about the acquisition of equipment. That's where we get also, say, money from the European Commission, which we put in place in order to make this equipment available then for use for scientific research, largely then for European users, and in particular also for users from the Human Brain Project. And that's what we call then the Fenix Infrastructure. Now, the approach which we are taking here is, I mean, the equipment which I was talking about is obviously equipment which is distributed over multiple sites throughout Europe, and we are planning to put a federation layer on top of it, which allows to access then to the different compute and data services, which are then provided at, for the time being, 5 different sites. In the future, it could be even also more sites. The idea behind distributing that is that within different research communities, in particular also within the human brain community, research community, we do have quite a different set of data sources, and we would like to have the data storage and compute capabilities close to these data sources, so not to put ourselves in a situation where we would have to move petabytes of data throughout of Europe. The underlying infrastructure services are going to be provided in a service-oriented manner, and they are currently, and I will explain it in more detail on the next slide, defined in a relatively generic form. It's the purpose to have here a generic infrastructure service layer, which meets then the requirements of different science communities, of course, with the human brain community being, say, the most important one. But we are also have the obligation as part of the contract which we have with the European Commission to also service other research communities. And on top of these infrastructure services, we then foresee that the different research communities put their community-specific platform tools and services. In case of the Human Brain Project, it will be, for instance, services like Collaboratory or the Knowledge Graph. And so what we want to achieve by having this federation of infrastructures is that we optimize for data locality, that we also enhance availability, because if one site is not available, for instance, due to maintenance, then other sites continue to be operational. But in this way, we also want to ensure that we have a broader variety of services and also know-how which we have available at the different sites. Now let's have a look in the more specific services which we are, say, offering. And one of the things which we did in this project is to actually come up with a relatively abstract description of the different services to allow for a different implementation of these services. So when it's here says scalable compute services, then it's obviously about HPC services, but it's not mandating a specific type of HPC service. So you will see here in the future different kind of architectures which are providing these scalable compute services. Currently, it's the Pitstein system at CSCS, and I will give you details on that later on. Then there is a service which for us supercomputing centers is a very new service. I mean, so far we are used to provide large-scale compute services through a batch queuing system. So you submit your job, and then at some point when the batch queuing system considers it suitable and fair, it will schedule your job. But we see a growing need from different communities, including the neuroscience communities, to have an also interactive access to compute resources. This interactive access basically means the ability, for instance, to log into a server from where you can interactively, for instance, analyze your data, but depending on also on the availability of the proper software tools, it would also allow to connect, for instance, to running simulations to have a more interactivity also with respect to scalable compute services. Then we have the virtual machine services, which basically, as the name says, is about giving you the opportunity to define, build virtual machines and to launch them as a vehicle then to deploy, for instance, platform services. And then finally, we have two different types of data storage services. We call them active data repositories and archival data repositories. Now, let me start with the second one. The archival data repositories are data stores which are meant to be used for a more long-term store, but they have a very important properties. These are data repositories which are federated. So these are the data repositories which also then facilitate sharing of data within a larger community. And essentially, all the other repositories we call active data repositories. You can, for instance, think about them as also the high-performance storage tiers, which we have in our different data centers, the parallel file systems based on GPFS and Lustre. They allow for having a replica of your data. Think about them as these being private copies because these are not data repositories which are federated. So they are not optimized for data sharing. They are much more optimized for providing high performance access to your data. So there will actually be a number of other services where I don't go into the details here. They're also still to come, and we will present them at later webinars, but maybe one to highlight before going to the details of these available resources is that we will also have services in place which allows you then, for instance, to move data between the different data stores. Now, but let's look in what kind of resources are available today. And this is basically the kind of resources for which you then can apply for using them. Currently, we have only one site which is providing resources. The background for this is that the other sites are still in the process of procuring the equipment, which is then going to be available next year for being used by you. So what do we have at CSCS? As you can see here in this table, we essentially have all the services which were introduced on the previous page. And they are deployed on different hardware components which are in operation at the Swiss Supercomputing Center. We have here in particular the large Bit-Stein system, which internally comprises two different partitions. One is the multi-core partition, and the other one is the hybrid partition. The hybrid partition has, except for a single CPU, additionally also a GPU in there. And they can be used for either scalable compute services, but you can also use the multi-core nodes or the hybrid node, sorry, for interactive compute access. Then there is another cluster which is used to run virtual machines. So if you are interested to build a virtual machine, to deploy it and to operate it, then you would run on the OpenStack cluster at CSCS. And then we finally have then the different storage types. We have an object-oriented data store based with a SWIFT interface, which is for having then the archival data repositories, in short, ARD. And then we have storage tier, which is optimized for high performance, which is the active data repository. And you can see here in these other columns what is the total amount of the resources which are available to ICEI. Then there's only a fraction of that is then being made available to the human brain. The fraction is 25%. Another 15% is then made available to praise. And the remaining 60% go to national users. There will also be resources at the other sites, but as already said, this is currently still in the process of being made available, and we are in some of the sites still in the process of procuring the equipment. Here at the UD Supercomputing Center, we have completed this procurement, and we are now starting in with deploying this equipment, expecting that this equipment will become available at the beginning of next year. And you have here on this slide a link to a website where we continuously update the available resources as soon as they become available. So let's look in more detail at the resources which are currently available at CSCS. As already mentioned, we have here this big Bit-Stein supercomputer, which internally is split in two partitions. One is a multi-core partition where each of the nodes comprises two server processors from Intel with then 18 cores. There are different memory configurations. Most of the nodes have 64 gigabytes of memory, and other nodes have 128 gigabytes of memory. Now, this system is not available, of course, for the Human Brain Project or ICEI for the full time. It's only a fraction of the system which is available to us. But given that this is, we have own as a Fenix a part of these resources, we can give then the user the ability to use the full capability of this system. So that means that users can, in principle, use up to 1,431 nodes in a single job. Of course, then only for a shorter period of time. Then there is an even larger partition, that's a so-called bit-stack hybrid partition. The main difference is that each node comprises then of a processor and then an NVIDIA GPU. So in this sense, it provides you significantly more compute capability, but it relies then on you being able to exploit the GPU. Here there are 5,320 nodes available. So here you have in principle the possibility to scale out to very large number of jobs. Then the archival data repository, as already mentioned, this is realized through an object store with a SWIFT interface, and this kind of interface will be used by all other IC sites as soon as they also deploy the archival data repositories there. So this is something where you then can use, which you can use then to share your data and to make them available also to a wider community. So how is the access to this infrastructure organized? In order to facilitate that, we have to put an allocation mechanism in place, and the European Commission expected from us to have here a mechanism which follows the peer review principle. That means that when you submit, when you want to have resources from IC, you have to submit a proposal. And this proposal is then being reviewed, and it follows then the principles which are, for instance, also have been established by PRAISE. So for those who have already been using PRAISE resources in the past, may have already, say, some understanding of how this process works. Now, there is, however, an important difference here, and that is that part of the resources are owned by the Human Brain Project. So it is the Human Brain Project itself who decides who get access to these resources. And these are, by the way, even so we as IC partners are part of the Human Brain Project, it's not us as supercomputing centers who decides about it, but these are, say, representatives of the Human Brain Projects. These are mainly also neuroscientists who manage this process of peer review and then also making a proposal of whether a project should be accepted and the resources should be granted. Now, out of these 100% of the infrastructure resources which become available through IC and Fenix, 25% of these resources are available to the Human Brain Project. 15% are going to be available to European researchers at large. And here we again put an entity in charge of making decisions about who gets access to these resources. So again, it's not the supercomputing centers who decide who gets these resources, but in this case, it's PRAISE, who is currently in the process of putting a committee of scientists together who will manage this process. And then there's a final 60%, which goes then to national users in the different countries which are involved in IC, because there's significant national funding also involved in this project. So if you are a member of the Human Brain Project, then visit the Fenix website and you will find there a flyer about access to Fenix IT services for HPC users, which explain then in more detail of how this works. For non-HPC members at this point of time, we have to ask you to be a little bit patient until PRAISE will, in the next weeks or a very few months, then publish a dedicated call where you can apply then for IC Tier 1 resources. So where are we moving to? So we are currently have different in the process of procuring different infrastructure components and expect them that they are operational at all the 5 IC sites in Q2 of next year. But in parallel, we also putting a number of other important services in place, which are needed to facilitate the federation of the services, or to also facilitate global management of users and resources at the federation level. And it's also about having services in place which makes it simpler to manage data within a distributed infrastructure. So to have data location and transfer services in place, and also to have a data mover service in place, where the data mover is a specific service for moving data within one site between the archival data repositories. Remember, these are the repositories which are federated, and the active data repositories, so that are the local data repositories where you can keep then private copies of the data for very fast access. Now, these services, they still depend on some development efforts to complete, so it will take some time of putting them in place. For the time being, we're trying to work around as good as we can in order to make sure that you can make best possible use of the hardware equipment, which we have put in place and which we are putting in place over the next 6 to 12 months. So bottom line is that the infrastructure is now open for users, not only from the neuroscience community, but also for other communities. So we would definitely also encourage other user communities to apply for resources then within the upcoming praise calls. Now let me conclude my part with a short example of one of our power users. Michele Migliore has been one of the early users of this infrastructure, which makes also very intensive use also of the HPC capabilities in order to study the hippocampus, so that's a specific area in our human brain. And the goal of the project is through numerical simulations to contribute to a better understanding of higher brain functions, which then would have all kinds of impacts in terms of fundamental research, of understanding of how our brains work. But the Human Brain Project obviously also hopes that this research will lead to also have impact more, for instance, in the medical area, to understand brain diseases, for instance. And as you can see here in this specific example, and it's a very good example to show that only having a supercomputer which allows to run scalable jobs is not sufficient anymore. We also have, of course, to provide fast data repositories, which we call in the IC language active data repositories. But we also have to provide the capability then to analyze this data or to visualize this data to, as you can see here in these very nice pictures. And that's where, for instance, the interactive computing services come into the game. And the data products which are created through the simulation should also become available to the research community so that they can use it then for their research. So the data products resulting from the simulation should eventually end up then in the archival data repositories, where they can make then can be made accessible then for other users. With this, I would then start with the second part of the presentation, which is then more specifically about the archival data repositories and technology on which they are based on, namely OpenStack SWIFT. And for this, I would hand over then to my colleague, Thorsten Harter.
So welcome from me too. Now we move to the technical details. And the first note is this technology is called OpenStack SWIFT, not to be confused with Apple's Swift programming language. This is important if you search up information on this topic, and I've stumbled on this numerous times. So with that out of the way, Swift is an object store, and most importantly, this is not a file system, and it's especially not a POSIX style file system. What does this mean? So objects in Swift are manipulated using the HTTP-based API in the form of post, put, and get requests against a defined endpoint. Here, the atomic units are objects, not files, and so there's no byte level access. These are the important characteristics if you want to differentiate between object stores and file systems. So there's a number of terms I have to define before we can actually talk about the methods of which are used to access Swift objects. So first, there's the endpoint, which is the top-level address of the installation you try to access. And these are different for different sites. And at the moment, we only have the installation at the CSDS called Pollux. The next level is the project and account level. These are used to group containers by creators and projects creators belong to. Next up is the container, and finally the object. And this is exactly the hierarchy we are talking about. There is no further subdivision between objects. There is no equivalent of directories. The only thing you have are containers. Although object names can contain a slash, which would signify in Unix-style file system a directory, these are ignored and are effectively only part of the name. This becomes confusing if you try to use an object store as a file system, but you can have an object that's called A and another object that's called A/B. So these are ignored completely. And finally, you can use object stores to share data between users. And for this, we have a number of ACL method access control lists, which are mainly used to regulate read, write, and list access. From here, I like to move to the even more specific how to access the CSDS Pollux installation. The first step you need to take is to obtain an account on Pollux, and if you follow the link here, you will learn how to do this. The next step is to create a Python virtual environment. This is not strictly necessary, but I like to do it to isolate this client from other projects I might have on my local machine. So this is a quite standard method to do this. You create it using the venv module, then you activate the virtual environment, and at this point you will notice that your shell prompt changes to indicate that you are inside the virtual environment. Next step is to install foremost the Swift client and the OpenStack client and a number of supporting libraries. And here on this slide, there's a small omission. You need to install the LXML library too. Next, you need to obtain a script provided by CSDS, which will allow you to set the environment variables necessary to access CSDS Pollux. Now then, you can leave the virtual environment by calling deactivate. So this is the one-time setup. And from now on, you can simply authenticate to Pollux by activating the virtual environment, which is done by sourcing the Pollux bin activate script. Again, the prompt changes. And now you can source the environment script called pollux.env in this case. You will be asked for your username and password, which I omit here for obvious reasons. And then you will be prompted with a list of your projects, which you can choose from. As soon as you have this step completed successfully, you can use the Swift command line tool. This is not the raw Swift command, but rather an alias, which is pre-configured to use your account prefix and the Pollux endpoint. Be aware of this when you're trying to do transfers from other sites or other accounts. In this case, you will need to omit the alias and use the raw Swift tool. So having authenticated, you can now use the actual object store. In this case, I show how a user on one side, on the left side in this case, might create a container which we fill with some bogus data for demo purposes, which is simply called demo data. And then you create a container called demo by calling Swift post. This is not strictly necessary and can be omitted by simply directly uploading the data, which we'll be doing in the next step. But for demonstration purpose, I like to show it in this case. Then you can upload data to the demo container, which is the first argument, and then you provide the directory you like to upload. And finally, you can check the contents of the container. And this is simply the contents of the directory, including the directory prefix of the data you uploaded. So having completed this step, you can move to another site, which might be another site you have access via SSH or something else. You can authenticate again and then call Swift list and see the contents of the demo container. And this can be downloaded by simply calling Swift download on the demo container. And again, if you try to add some data to this container, you can create the data and call upload again and provide the container as an argument. And if you'd like a specific object name, you can pass this again as an argument. This is a very short introduction how to interact with Swift. You can see more on the wiki link provided below, and there's more content coming up here. Another important caveat when using object stores is that the performance you achieve strongly depends on the object size that is processed. In this case, I've procured some performance numbers on CSS Pollux, which has been generated using a tool called CostBench. And in particular, this is a tool provided by Intel in the original, I believe, but this is using the OpenIO fork because the original didn't work for me. It's using a concurrent mix of 80% reads and writes and 20% writes. And here we can see that about an object size of 4 megabyte will be the saturation of the bandwidth we can achieve. And also note there's a difference in performance between reading and writing. So these are numbers to keep in mind when designing your interaction with the object store. This means there's a lower limit on the objects you should use for best performance. If you need to get help with technical issues, you can contact the support at humanbrainproject.eu email address, and this is the central turning point for all support requests. It will provide first and second level technical support with Fenix services and site local requests. And also there's the advanced support by the high-level support team of the Human Brain Project, which includes guidance for preparing applications in the Human Brain Project, and also the implementation of workflow and simulations for Fenix. And with this, I come to the end and would finish the presentation.
Okay, thank you very much both for your presentation. So we can allow the ground for questions now.
Hello, can you hear me?
Mm-hmm.
Yes.
Hi, this is Pablo from the UPM. I just wanted to maybe ask you how this approach suits with maybe interactive visualization applications. I don't know if you can give me any details about that.
Well, from the perspective of splitting it between infrastructure services and platform services, the visualization services would for us act on more at the platform level, because many of the visualization services are tend to be more also domain specific. And in the context of how we define, say, the infrastructure services, at this point, there are two options. I mean, either one deploys a service in a VM and can make that then very openly accessible also through a web interface. The alternative is to use then the interactive computing services, which are then inside also then the HPC domain, where you then would have say faster access also to the data, but then the access mechanisms would be a bit more limited, as you would have to tunnel then out of the more secure domain. So this is certainly an area where we would have to work on say, providing here also reference implementations. But I would currently also encourage everybody who is developing services within the Human Brain Project to look on, to consider applying for VM resources. I mean, we're talking then here not about a lot of resources, so it's just a relatively simple application which needs to be submitted. It will not run through a complex peer review mechanism. It will just be looked at from a technical perspective. And we have recently seen a relatively quick turnaround through our infrastructure allocation committee of the HBP to grant then access to these resources. And you can also use these mechanisms to get resources for development efforts.
Okay, thank you.
So just to thank our partners, Dirk has already mentioned them earlier on in his presentation. I would like to announce our next Fenix webinar, which is taking place on the 10th of December on Tuesday at the same time, 3 to 4 p.m. And it is going to be on how to exploit the ICEI scalable compute services for neuroscience research. And we will share more details on our website and media about this soon, so that you can register if you are interested. And a final note, again, as Dirk mentioned, on our media channels, you can visit our website to find out about the Fenix Infrastructure Services, resources, and how to access. And also you can find us on Twitter for any updates about the project. For any questions, you can send us an email and you will receive a follow-up email after this webinar. Thank you all very much for attending, and we hope to see you at our next webinar.